All right, here's example number 3, the final example. Like I alluded to, there are a couple curveballs here, so let's go ahead and read the example and then we'll talk about how to tackle this problem. Determine the empirical formula of a compound that contains 36.5% sodium, 25.4% sulfur, and 38.1% oxygen. So as you can see, this is our first example that has more than just 2 elements. So we will have to set up multiple mole ratios in order to get the ratio of atoms in this compound. And then instead of given grams or moles, we're given percents. So the easiest way to tackle a percent problem is to go ahead and assume go ahead and assume 100 grams of your compound. Because if you assume 100 grams of your compound, then if you have 36.5% of 100 is 36.5 grams of sodium. And then we can get that to moles. And if 25.4% is sulfur, 25.4% of 100 is 25.4 grams of sulfur. So we can get that to moles. And then if 38.1% is oxygen, 38.1% of 100 is 38.1 grams of oxygen. So we can get that to moles. So looking up on your periodic table, let's get the molar masses of each of these elements. Sodium has a molar mass of 22.99 grams. So 36.5 divided by 22.99, we get 1.588 moles of sodium. The molar mass of sulfur, 32.07 grams of sulfur in 1 mole of sulfur. 25.4 divided by 32.07, and we get 0.7920 moles of sulfur. And then the molar mass of oxygen, 16 grams in 1 mole of oxygen. 38.1 divided by 16, 2.381 moles of oxygen. So we now have 3 different moles. Our lowest moles are sulfur. So what we're going to do is we're going to set up 2 mole ratios. Sodium over sulfur. And oxygen over sulfur. So if I take 1.588 divided by 0.7290, so I'm looking at moles of sodium to moles of sulfur, and I get a 2-to-1 ratio, so 2 moles of sodium to 1 mole of sulfur. And hopefully you realize that it's super important to put your substances, because if you just put 2 moles over 1 mole, you may mistakenly put more sulfur than sodium. So again, those good habits make the problems a little bit easier to reason through. All right, and now oxygen, 2.381 divided by 0.720. And we have 3 moles of oxygen to every 1 mole of sulfur. So I could do a mole ratio of sulfur over sulfur, but it's going to be a 1-to-1. And if I have 2 moles of sodium to 1 mole of sulfur and 3 moles of oxygen to 1 mole of sulfur, can I then say I have 2 moles of sodium to 3 moles of oxygen? And the answer is yes. So we now know all of the mole ratios. We know all of the ratios of atoms in our compound, so we're ready to write our empirical formula. So is this an ionic or a covalent compound? Hopefully you said ionic because we have sodium. We always give our metals first, so our 2 sodium are going to come first. We then have 3 moles of oxygen to 1 mole of sulfur in this compound. Those are both nonmetals, so that's covalent. So you could put it in any order you want, but hopefully you recognize that you have sulfite here with SO3. I'd never take off points for putting the oxygen before the sulfur, but I will be thrilled if you recognize that it's a polyatomic ion sulfite. So there's our empirical formula, Na2SO3. So determine the molecular formula if the molar mass is 126 grams. So we need to get the molar mass of our empirical. We have 2 atoms of our sodium with a mass of 22.99 grams. We have 1 atom of sulfur, and we have 3 atoms of oxygen. And we get a molar mass of 126.05 grams. Our actual mass is 126 grams, so our empirical is our molecular formula. And that's probably not surprising. Sodium has a +1 charge. Sulfite has a 2- charge. So I'm going to need 2 of those to be neutral, which is our formula. Whoops. Now, we've been getting whole numbers with our ratios. Occasionally, you will not get whole numbers. So what if you get 2.5 moles of carbon to 1 mole of oxygen and 3 moles of hydrogen to 1 mole of oxygen. We can't round this because it's not close to a whole number. I really would only round if I'm a little bit higher or a little bit under, within 0.1. I might round, but I would not round in this case. So if I use the numbers given, I get C2.5H3O. The problem is I can't have a half atom of carbon, so I really have to get rid of that 0.5. So I'm going to distribute a 2 to get rid of that 0.5. So my actual empirical formula, C5H6O2. Now, is that still empirical? Is that still an empirical formula? And the answer is yeah, of course. And what we really have are 5 moles of carbon to 2 moles of oxygen, which would be a 2.5 to 1 ratio, as we saw right here. So if you're really close to a whole number, within a tenth, rounding is fine. If you're not, you're going to have to figure out what you have to multiply for, by in order to get rid of the decimal. So like 0.33, you would multiply by 3. 0.25, you would multiply by 4. But you don't want to round these or you'll end up with the wrong formula. All right, so there we are, empirical formulas. We did 3 different examples, a little bit of curveball in each. Now it's time to go practice and master this process.